I mean, think about it. An AI can code a totally flawless, fully functional game of Snake in Python in like 2 seconds.
Yeah, literally instantly.
Right.
Mm-hmm.
But if you ask that exact same AI to update, a single billing module in your company's legacy code base, it will confidently and almost joyfully just break your entire application.
Oh, completely shatter it.
Exactly. So for today's deep dive, we are unpacking why artificial intelligence suddenly becomes completely incompetent the absolute second it touches a real-world enterprise system.
Well, basically because building a toy app from scratch is, it's a completely different physics engine than modifying a 10-year-old monolithic application.
Yeah.
And that is exactly what we are dissecting today. We've got this amazing boots-on-the-ground systems write-up from an engineer who actually spent months running coding agents like specifically Claude Code and Codex on actual high-stakes production systems.
Which is rare to see, honestly.
Totally. We are talking about an EV charging management platform and this really complex ad production platform. Real stuff.
Which means we are finally moving past the flashy vendor demos. You know the ones, right? Where someone opens this pristine, totally empty terminal and just types, build a website.
Right. And it feels like literal magic.
It does. But it's like watching a master chef in a Spotless test kitchen where every ingredient is pre-measured in little glass bowls.
Oh, that's a perfect way to look at it.
Yeah, because stepping into a real code base is like walking into a messy restaurant kitchen during a Friday night dinner rush. Like, half the staff is using shorthand you don't understand, the menu changed 3 times today, and someone duct taped the walk-in fridge shut in 2019, and nobody knows why.
Exactly. That environmental chaos is just the perfect way to frame it, because to understand why standard AI agents fail in that messy kitchen, we have to, establish a baseline reality of what an AI coding agent actually is, mechanically speaking.
Okay, let's unpack this.
So a modern agent is basically just a large language model with an enormous context window, like maybe hundreds of thousands of tokens. It can hold a massive amount of immediate information in its working memory, but it has absolutely zero persistent state outside of that specific session.
So no matter how brilliant it is, every time you spin up a new task, it's waking up completely blank.
Exactly.
It doesn't know what architectural decisions your team made 3 months ago. And worse, from what the source notes anyway, its confidence has basically zero correlation with its correctness.
None at all. It will propose completely contradictory architectures from one session to the next without even blinking.
Which is wild.
Yeah, and the author makes a really crucial point right up front here. These aren't bugs.
Wait, really?
No, I mean, the amnesia and the hallucinations, they are not software defects that are just going to be patched out next week by OpenAI or Anthropic. This is just the fundamental shape of the technology.
Wow.
You're dealing with a stateless prediction engine that is trying to operate in a highly stateful environment.
Okay, so if I'm managing this stateless prediction engine, my first massive problem is just getting it to look at my code without drowning.
Right.
Because a human engineer reads code with intent.
Right.
You look at a function, you jump to its definition, you trace a specific error. But agents don't natively do that.
No, they don't. By default, if you just drop an agent into a terminal, it uses basic text commands. Like it uses grep to search for text strings or cat to print out file contents.
Which is fine for a toy app, but...
Right. But if your project has thousands of files, those raw commands return massive, just noisy walls of text.
Yeah.
So the agent ends up burning its entire context window just trying to read a few files, and it pushes out the actual problem it was trying to solve in the first place.
Which brings us to the first major piece of infrastructure the author had to build to solve this. They call it giving the agent sight.
I love that term.
Me too. Because instead of letting the AI blindly grep the code base, they built this dedicated code intelligence service exposed via the Model Context Protocol, or MCP.
Yeah, and for those who maybe haven't implemented it yet, MCP is essentially a standardized way for AI models to connect to external tools and data sources.
Right.
So the author used it to build 7 very specific tools that essentially intercept the agent's need for information and serve it up surgically.
And 2 of these tools really caught my attention because they totally changed the mechanics of how the AI works.
Oh, definitely.
The first one is repo context. Basically, if the agent realizes it needs to understand a specific function, say like process payment, it doesn't just download the 2,000-line file that houses it.
Right, because that would blow up the context window.
Exactly. The repo context tool goes into the file, extracts only that specific function, grabs the immediate surrounding scope so it makes sense, and returns just that snippet.
It's acting as a scalpel.
Yeah.
It preserves the context window so the agent has plenty of cognitive space left to actually solve your problem. But the second tool you mentioned, well, it's arguably the most important piece of the entire stack, repo impact.
Oh, man. Hold on, because repo impact is basically acting as this massive safety net.
Totally.
The author explicitly claims this one tool has killed more bad refactors than any human review process they've ever run, which is a huge statement. How is it actually doing that?
So it analyzes the blast radius of a proposed change before the change is actually committed.
Okay.
When an AI agent wants to modify a function signature, let's say it wants to add a new parameter to your user authentication module, it usually only looks at the immediate file. It thinks, oh, this looks fine.
Right, it doesn't know about the rest of the app.
Exactly. What repo impact does is trace the dependency graph. It automatically scans the entire code base to see every single place that calls that specific function.
So it basically immediately flags the, 47 other places in the code that rely on the old signature, which the agent didn't even know existed.
Precisely. Without repo impact, the agent just changes the signature, assumes it did a brilliant job, and quietly breaks 47 different endpoints. Yeah. The tool forces the AI to confront the architectural reality of its decisions before it acts.
I mean, the author describes an agent without these MCP tools as just a junior developer with no IDE, no jump to definition, and a flashlight.
Which is a terrifying thought.
Truly terrifying if they are touching your production database.
Yeah.
But here's where it gets really interesting. If MCP is the standard protocol here, does that mean the tooling is model agnostic? Like if a brand new, vastly superior AI model drops tomorrow, can you just plug it into this same flashlight?
What's fascinating here is that the answer is yes.
Oh, wow.
And that exposes this huge shift in how we need to think about AI development right now. Treating this as an infrastructure problem rather than an AI model problem means your tooling investment compounds.
Right, it doesn't get obsolete in a week.
Exactly. Whether you use Claude today, Codex tomorrow, or something else entirely next year, if it speaks MCP, it instantly inherits this localized intelligence.
Okay, so MCP solves the vision problem. The agent can surgically read the code today. But what happens tomorrow when I log back in?
Ah, the memory problem.
Right, because if the agent resets its context window every single time, those eyes are kind of useless because it completely forgets everything we decided yesterday.
Yeah, and this is where we hit what the source author calls the absolute biggest trap in modern AI coding.
Which is?
The myth of the single vector database.
Whoa, back up. Vector databases are basically the gold standard for AI right now.
I know, everyone uses them.
Right. Every tutorial, every vendor pitch says that if you want your AI to have memory, you chunk your documents, create embeddings, and dump them in a vector store. Why is the author calling that a trap?
Well, because a vector database is fundamentally an engine of semantic similarity.
Okay.
It operates on fuzzy matching. If you ask a vector database, hey, find me prior discussions that are sort of related to user authentication, it is brilliant. It maps the conceptual proximity of those words and returns relevant text chunks.
But software engineering isn't fuzzy.
Exactly. It does not run on fuzzy concepts. It runs on exact hard-coded contracts and very explicit logic paths.
So, like, if I ask the agent for the specific architectural rule we agreed on yesterday for handling API rate limits, a vector database might return, what, a paragraph from last month that just sounds like the rule?
Yes. It sounds like the rule, but it isn't the actual current rule.
Which is almost worse than useless.
It is worse because the AI will confidently implement the outdated, almost correct rule and just subtly corrupt your system.
Wow.
But the author points out an even more catastrophic failure mode here, graph queries.
Graph queries meaning, like, chains of connection.
Yeah.
Like module A depends on module B, which depends on module C.
Exactly. So let's say the agent asks, what depends on this specific piece of code, scene blueprint?
Okay.
A vector search cannot answer that structurally. It will just return random, totally disconnected chunks of text that happen to contain the string scene blueprint.
Ah, so it might give you module A, but completely miss module C.
Exactly. The agent gets a noisy, incomplete approximation of your architecture, misses 3 real dependencies, and ships a broken feature. Basically, the underlying architecture of your memory system must match the structural shape of the query.
So how are they actually fixing this? Because the source outlines a pretty intense setup here, this hybrid memory platform.
Yeah, they did something incredibly pragmatic. They put multiple entirely distinct database paradigms inside a single PostgreSQL instance.
Wait, putting a vector database, a graph database, and standard relational tables all inside one Postgres instance? Doesn't that create a massive bottleneck? Like, why not use separate specialized databases for each?
I mean, if you were building a massive consumer web app, maybe, but for an AI agent loop, network latency and operational overhead are the real
Well,
enemies.
that makes sense.
Yeah, if you have three separate distributed databases, keeping them perfectly synced during rapid AI iterations is just an absolute nightmare. By using Postgres as the unified shell, they get ACD compliance across everything.
Okay, so break down how the agent actually uses this hybrid setup in practice.
Sure. So first, they use standard PostgreSQL relational tables for exact lookups.
Right.
When the agent needs a specific identifier or a strict structural contract, it queries the relational table. It gets a deterministic exact answer.
So relying only on a vector database is like asking my lawyer for the exact text of my contract, and instead they read me 5 poems that sound like my contract.
Yes, that is exactly what it is.
And the relational table actually gives me the contract.
Precisely. Then, right next to it, they use a Postgres extension called pgvector for semantic similarity.
For the fuzzy stuff.
Right, that handles the fuzzy searches. If the agent needs broader context on how you tackled a problem previously, it uses pgvector.
And what about the dependency chains, the whole graph problem?
For that, they use an extension called Apache AGE, which actually allows Postgres to act as a graph database.
Oh, neat.
A graph database maps data as nodes and edges literal connections. So when the agent asks, what breaks if I change scene blueprint? Apache AGE traverses the edges and returns the exact unbroken chain of dependencies. A depends on B, depends on C.
That's brilliant. And the source also mentions putting Redis on the hot path for cached lookups, all fronted by a FastAPI layer.
Right. Redis handles caching, so you aren't hitting the database disk for the exact same query 100 times a minute.
Makes sense.
And the FastAPI layer is crucial because the agent itself doesn't need to know it's interacting with 3 different database paradigms. It just sends a query to the API.
And the API routes exact questions to standard Postgres, fuzzy questions to pgvector, and relational questions to Apache AGE.
You got it. You fix the memory by building the right infrastructure to support the specific type of recall the agent needs at that exact millisecond.
Which perfectly brings us to the operational reality. We have the map, so it can see. We have the hybrid memory, so it can remember accurately. But how do you structure the actual minute-to-minute work? Because if I'm working with a human engineer, I don't just dump a memory bank and a map on their desk and walk away.
No, of course not.
There is a workflow. We have stand-ups, we leave comments on pull requests. Heck, if I'm just managing my own messy desk, if I don't leave myself a sticky note before I log off for the weekend, I have literally no idea what I was doing on Monday morning.
Yeah, and if you need that as a human with persistent biological memory, an AI agent needs it 10 times more.
Right.
The author solves this with component 3 durable session artifacts. You have to establish an ironclad written contract between sessions.
The source outlines 4 specific artifacts they maintain for every single unit of work. There's a plan, a tracker, a build log, and a handoff note.
Right.
The plan dictates the success criteria, the tracker acts as the current status, and the handoff note bridges the sessions. But the detail that really struck me was inside the build log.
Ah, the negative space.
Yes. The author insists that the build log cannot just record what the agent successfully built. It must record the specific reasoning for rejected ideas. Why is that negative space so critical?
Because negative context is exactly what large language models lack the most.
Really?
Yeah, think about how an LLM actually works. It predicts the next most likely token based on its training data. If a specific approach to a problem is statistically common on GitHub, the agent will naturally gravitate toward it.
Right, it wants to do the average thing.
Exactly. But if that average approach doesn't work in your specific quirky legacy code base, the agent hits a wall.
And if you don't document why it hit that wall.
Tomorrow, a new session starts. The agent looks at the problem, statistically predicts that the exact same broken approach is the best idea, and enthusiastically runs straight into the exact same wall.
Oh, that sounds endlessly frustrating.
It is. Documenting the reasoning for rejected ideas in the build log breaks that loop. It manually overrides the agent's statistical biases with your project's historical reality.
That makes total sense. And it's not just about tracking the status of a specific feature either. It's also about enforcing the overarching laws of the entire code base.
Right.
The author uses a specific file called CLAUDE.md, which basically functions as absolute architectural law.
Yeah, it's a non-negotiable manifesto. It enforces core engineering principles for your specific team. Things like no silent fallbacks when an API fails, or no hard-coded magic numbers, or observability logging must be built into every new function.
Stuff humans usually forget too.
Exactly. The agent is forced to read this file and internalize those constraints at the very beginning of every single session before a single line of code is evaluated.
Which raises a really interesting philosophical question about management.
Oh,
And so what does this all mean? If I build all of this, the artifacts, the rules, the CLAUDE.md file, and the agent goes rogue anyway and hard codes a bunch of magic numbers, bypassing the rules, whose fault is it? Is the AI just hallucinating again?
well, this is where the author introduces a very strict, almost uncomfortable philosophy for engineers to adopt.
Okay.
If the agent breaks a principle, it is treated entirely as a workflow failure. It is not an agent failure.
Meaning the human messed up.
Meaning the scaffolding you built didn't enforce the law hard enough.
Wow.
Look, the agent is a statistical engine. It does not have morals. It doesn't, respect your rules out of a sense of professional duty.
Right.
If it bypassed a rule, it means your automated testing hooks, your session artifacts, or your prompt structures just weren't rigorous enough to catch the deviation and autocorrect it. The infrastructure failed to contain the statistical variance of the model.
That is a wildly different mindset. You can't just shrug and say, oh, well, AI is weird sometimes. What can you do? You have to take complete ownership of the guardrails.
Exactly. And that philosophy is put to the ultimate test when you scale this up. We've built the map, the hybrid databases, the stripped session docs. What happens when we turn this whole machine on and put it under the stress of a massive production environment?
Right, because the source introduces this multi-agent alternation pattern,
Yeah.
which I found fascinating because they aren't just using one AI model to do everything. It's a tag team effort.
Yeah.
And it's actually slightly adversarial.
Adversarial by design. So here's the workflow. Claude Code starts the session. It reads the architectural law in CLAUDE.md. It reads the state from the 4 artifacts, and it begins executing the work.
Okay.
When it needs context, it queries the hybrid memory. When it makes an architectural decision, it commits that decision back to the Postgres database. Once the work is done, it writes a wrap-up note.
But then the baton doesn't get passed back to the human for review.
No.
It gets handed to a completely different model family Codex.
Yes. Codex steps in purely to review the work Claude just did. And the crucial mechanism here is that Codex uses the exact same memory layer, the exact same MCP code intelligence tools, and it judges the work against the exact same architectural law.
Okay, wait, why use 2 different models? Like, why not just have Claude review its own work?
Because models have inherent biases and blind spots based on their specific training architectures. Claude might have a blind spot regarding a specific edge case in Python memory management. If Claude reviews its own work, it will miss the error twice.
That makes perfect sense.
Right. By bringing in Codex, which has a fundamentally different underlying architecture, you are intentionally introducing a second perspective that does not share those same statistical blind spots.
I love this dynamic. It's like pitting 2 brilliant, highly caffeinated, maybe somewhat arrogant lawyers against each other to argue a case. They have the same evidence, the same case law, but completely different analytical approaches.
Yeah.
And the human just gets to sit back on the bench and be the judge.
And that tension is the feature, not a bug. The author explicitly notes that the highest signal moments in this entire workflow are when the 2 models disagree.
Because if 2 completely different AI brains looking at the exact same rules and the exact same code come to fundamentally different conclusions about whether a pull request is safe, that's a massive red flag.
Exactly. It highlights the exact spots where the code is ambiguous or the architectural rule is poorly defined. It pinpoints exactly where human intuition is actually required.
So the human isn't totally out of the loop.
Not at all. The human stays in the loop strictly for high-level architectural decisions, updating the principles in CLAUDE.md and settling these agent disagreements. Everything else, the boilerplate generation, the standard refactoring, the syntax checking, is distributed to the machine infrastructure.
It frees the human up to stop being a syntax checker and start being a true systems architect.
Yeah, and if we pull back and connect this to the bigger picture of where the industry is heading, the specific models we are using right now, like Claude, Codex, whatever else, they are temporary.
Sure.
They will inevitably churn. They will be replaced by faster, cheaper, vastly more capable models in 6 to 12 months. But the author's core realization remains completely unchanged, regardless of how smart the models get.
Which is that persistent state, Code intelligence and adversarial review are not AI problems.
Exactly. They're infrastructure problems, and they remain the human engineer's responsibility.
Right.
If you rely purely on the native intelligence of the next generation of models and you don't build this substrate, you're basically just going to accumulate invisible technical debt at light speed. You might post incredible development velocity numbers for a month, maybe two.
But then,
Eventually, the whole house of cards comes down because nobody, neither the human nor the machine, actually remembers how the complex system works or why decisions were made.
the agents are just the raw compute. The infrastructure is what translates that compute into real, durable engineering.
Perfectly said.
Okay, let's pull all of this together for the listener. Because if you want to use AI to ship actual software, not just build shiny prototypes in an empty test kitchen,
Yeah.
you can't just rely on the AI's brain. You have to build an entire nervous system around it.
Right.
You need the model context protocol tools to give it sight. So it isn't just blindly grepping your files and burning its context window. You need a deeply structured hybrid database mixing relational Postgres, semantic pgvector, and graph-based Apache AGE to give it a memory that actually understands exact facts and relational dependencies, not just fuzzy approximations.
Right.
And you need strict session documents and architectural laws to enforce a workflow that captures both what worked and, crucially, what failed.
It is a profound shift in how we think about software development. I mean, we're moving from writing code to building systems that manage entities that write code.
It really is.
But, examining in this architecture does leave me with one final, slightly unsettling question to consider.
I figured you were building up to something. What is it?
Well, look at the sheer scale of what we just discussed. Right now, to make an AI functionally reliable in production, we are having to build incredibly complex, multi-layered infrastructure. We are deploying graph databases, integrating adversarial multi-agent review loops, and maintaining rigorous session state machines, all just to manage the amnesia and the hallucinations of today's models.
Right. We are building a massive, highly intricate scaffolding just to control the builder.
Exactly. It's an enormous amount of overhead. So what happens when this management layer itself becomes so incredibly complex that humans can no longer fully comprehend the very scaffolding we built?
Oh, wow.
If the AI is the black box, and our solution is to surround it with an infrastructure so dense and complex that it can tame the black box, could the infrastructure itself become the next black box?
That is heavy, because we started this deep dive by talking about a messy restaurant kitchen. And it's one thing to bring in a highly efficient robot to chop the onions.
Right.
It's another thing entirely when you realize the operational manual for managing the robot has become 1,000 pages long, written in a language you barely speak. And you no longer understand the system that's telling the robot what the menu even is.
It's the absolute next frontier of technical debt.
And it is definitely something to keep an eye on. Well, thank you for joining us on this deep dive. Whether you are actively coding enterprise software, managing a technical team, or just trying to organize your own wildly chaotic life, take a moment today to think about how you structure memory and rules in your own daily workflows. What happens when your context resets? See you next time.